At the smallest scales of reality, matter is constantly engaged in a violent dance. Particles snap together with incredible force or throw each other apart. These pushes and pulls are governed by an invisible web of electric fields. Because human eyes can't actually see this web, the rules of electromagnetism can be difficult to visualize. For centuries, physicists were forced to deduce these invisible interactions blindly, relying on the tiny movements of delicate brass needles inside glass torsion balances. An educational poster from a physics institute in India has bypassed the heavy academic approach. It translates the cold, abstract math of electromagnetism into a language every human intuitively understands: romance. We are going to decode the mathematical equation that governs these forces through the lens of relationship drama. The actors in our equation are simple. We have a positive charge, represented here as the boyfriend, and a negative charge, the girlfriend. The poster lays out the terms of their engagement in Rule 1. Opposites attract, creating instant chemistry. In physics, fundamental particles have inherent properties that force them to actively seek out their energetic opposites to achieve stability. But what happens when you put two identical charges in the same space? Instead of chemistry, you get immediate repulsion. They push each other away. The poster captures this interaction in Rule 3. When two positive charges meet, they remain in a permanent friend zone. The specific identities of these charges, the variables Q1 and Q2, determine the initial potential for any interaction. They are the initial spark. Every initial spark faces a natural physical enemy, the space between them. As Rule 2 points out, giving credit to the physicist Charles Augustin de Coulomb, attraction decreases as the distance between the two parties increases. This spatial gap is represented in our equation by a denominator, r squared, or radius squared. This creates a geometric decay that is much sharper than a standard linear fade. This line graph visualizes the inverse square law. Doubling the distance between two charges drops the attraction down to a quarter of its original strength. This math explains why long-distance dynamics fade much faster than our intuition usually expects. Distance dictates the survival of the connection, acting as the unforgiving physical boundary limiting the interaction. Which brings up a mechanical problem. How do these charges actually reach across that empty space to pull on one another without ever touching? The poster answers this by drawing physical lines flowing directly through the empty space between our characters. This aligns with Rule 4. The stronger the electric field, the stronger the feelings, the physical force transmitted between them. In this vector field diagram, we can see exactly how this works. One charge acts as a source, altering the fabric of space around it. When a second charge enters that space, it physically feels those alterations and is pulled along the invisible tracks. The electric field is the invisible infrastructure of the universe. It translates a particle's mere existence into a tangible force felt by everything around it. Here we have the complete mathematical expression of Coulomb's law, assembling on screen. The initial chemistry of our two actors sits on top as Q1 and Q2. The steep, long-distance drop-off sits on the bottom as r squared. The feelings that bridge the gap make up the resulting force. The microscopic world operates on predictable rules of engagement that mirror the macro world we live in. By applying the logic of human connection to these particles, the core mechanics of electrostatic force become much clearer. It turns out, physics offers some of the most reliable relationship advice of